Welcome back, everyone. We're about to begin the second session of today's presentation with regard to LNG operations, safety issues, and procedures. This presentation's agenda includes some definitions, a brief overview of the LNG market, then we move forward to LNG issues, property, hazards. We discuss the elements of safety, the LNG value chain and the LNG facilities, while we move forward to LNG operations by describing the transfer procedures, the pre-bunkering operations, the bunkering operations and the after-bunkering procedures, while we finally close our presentation with the regulatory framework and some relevant conclusions. Now, for starters, to the definitions. Bunkering loading temperature. Atmospheric pressure, natural gas will liquefy at the temperature of about -162 Celsius. As LNG increases in temperature, its vapor pressure increases and its liquid density decreases. These physical changes need to be considered because they may increase the required storage tank volume and pressure rating. The filling rate. The filling limit. The filling limit of an LNG tank is the maximum allowable liquid volume in the tank expressed as a percentage of the total tank volume. The filling limit is not the same as the loading limit. The maximum filling limit for LNG cargo tanks is 98% at the reference temperature. This same limit is expected to apply to LNG fuel tanks. A higher filling limit may be allowed on a case-by-case basis based on requirements from classification societies and regulatory bodies. Reference temperature. The reference temperature is the temperature corresponding to the saturated vapor pressure of the LNG at the set pressure of the pressure relief valves. For example, if the LNG tank has a pressure relief valve set pressure of 0.7 bars, then the reference temperature is 154.7 degrees Celsius, which is the temperature that natural gas will remain liquid at 0.7 bars. Loading limit. The loading limit is the maximum allowable liquid volume to which the tank may be loaded, expressed as a percentage of the total tank volume. This limit depends on the LNG densities at the loading temperature and reference temperature. The hill. The hill is the volume of LNG that is normally left in the tank before bunkering is called the tank hill. This small volume of LNG keeps the LNG tank cold before it is refilled during bunkering. The required tank hill should be calculated with the assistance of the tank designer and fuel gas designer based on several variables such as the tank size and shape, ship motions, heat inflow from external sources, gas consumption of the engines, and bunkering and voyage schedule. As a general rule of thumb, for initial design considerations, a tank hill of 5% can be assumed. Usable capacity. In general, the usable capacity of the LNG tank is equal to the loading limit minus the hill, expressed as a percentage of the tank volume. The usable capacity is the consumable volume of bunkered LNG in the tank. Moving to the LNG market overview. The LNG market remains buoyant as all of the major importing regions are seeing increases in LNG imports since 2011, accounting nearly to 10% on a year-over-year basis. An even greater growth in global LNG trade is largely slowed down mainly due to constrained export capacity. So, despite being in need of increasing volumes of LNG in the short term, there will not be a major growth until gains from projects around the world and especially Australia begin to come on stream. Ship demand, as we observe also in the graph, ship demand growth will continue to exceed fleet growth for the following years, while the overall vessel supply surplus is moving roughly between 10 to 20%, as we can see in the figure, range across the 2010-2015 horizon. The majority of LNG trade is carried out through sea and mainly through the following countries: from Libya to Italy and Spain, from Algeria to France and UK, from West Africa to Northern Europe and more specifically to Belgium and Netherlands, from Alaska and Australia to USA and Japan, from Borneo and Venezuela, again in USA and Japan, from the Persian Gulf to USA and Japan, and finally from Saudi Arabia to the same destinations again, USA and Japan. Here we see the picture with the LNG main trade routes. As we said previously, the main trade routes include from Australia to Japan and South Korea, from Japan to the Gulf of Mexico and more particularly to Lake Charles and North America to the Cove Point, from West Africa and Nigeria to Europe and USA, while also from Saudi Arabia to the Southeast Asian countries and to Northern Europe. In this picture, we can see the LNG facilities, the existing and the possible LNG facilities in the Pacific Rim. As we can observe, there are only a few, 3 in the number, existing LS3 regasification terminals and around 5 existing LNG liquefaction terminals. The prospects for the future are growing, as we can see, because there are around 6 possible projects of 6 possible regasification projects underway and 2 possible liquefaction projects, which shows that the future of LNG and the potential and the prospects are growing very fast. Now, moving to the LNG issues, properties and hazards. One of the main reasons for building vessels fueled with LNG is their environmentally friendly profile, both under normal operations and in the event of an accident. Using LNG instead of diesel is more environmentally friendly for the following reasons. Burning LNG as a fuel instead of diesel reduces the greenhouse gas emissions, CO2 and HC, due to the higher hydrogen ratio in LNG compared to diesel, or HFO. The release of NOx and SOx in practices are reduced significantly to 82 to 84%, 100% and 65% respectively. The reductions are dependent on engine size and type. Methane gas might be released through the vent must due to different reasons such as pressure built up in the LNG tank. Methane is a more severe greenhouse gas than CO2, greenhouse potential 20 to 25 times greater than CO2, and therefore methane releases should be kept to emergencies only. Running the engines or boiler on gas to lower the pressures in the LNG tank is better for the environment than lowering the pressures by releasing methane. The most likely source of methane releases will be due to purging of the gas pipes to ensure that no gas is trapped. This will be done when shutting down the engines or switching to diesel fuel. The amount of methane gas released in these scenarios will most likely be minor, as well as the frequency thereof. Accidental spills of LNG to the marine environment would result in a relatively small and thin film, which is which is so volatile it would only affect the immediate surroundings. The majority of the fuel would evaporate immediately and be removed from the sea. Comparatively, a diesel oil release of the same magnitude, same mass of fuel, would result in an oil slick about 1000 times larger, more persistent, and much more detrimental to sea mammals, birds, and aquatic wildlife. Releases of subsurface LNG, a worst-case scenario for releases to the aquatic environment during capsizing, would result in a gaseous flow to the surface of methane and ethane, which would saturate the surrounding waters with these gases. The concentrations are not, however, considered sufficiently high to cause long-term effects on the affected environment. The components that may be liquid at deeper waters, butans and pentans, have such a low density that these two are expected to flow rapidly to the surface if released after capsizing or sinking the vessel. Rapid dilution of these components to concentrations well below acute chronic effect levels ensures that negligible environmental effects are expected from such a spill. Issues for LNG operations concern various aspects. The LNG industry has an excellent safety record. This strong safety record is a result of several factors. Firstly, the industry has technologically and operationally evolved to ensure safe and secure operations. Technical and operational advances include everything from the engineering that underlies LNG facilities to operational procedures to technical competency of personnel. Secondly, the physical and chemical properties of LNG, as described above, are such that risks and hazards are well understood and incorporated into technology and operation. Third, the standards, codes, and regulations that apply to the LNG industry further ensure safety. While we in the US have our own regulatory requirements for LNG operators, we have benefited from the evolving international standards and codes that regulate this industry. LNG industry consideration and mitigation and risk mitigation. The LNG industry is subject to the same routine hazards and safety considerations that occur in any industrial activity. These mitigation systems must be in place to reduce the possibility of occupational hazards and to ensure protection of surrounding communities and the natural environment. As with any industry, LNG operators must conform to all relevant national and local regulations, standards, and codes. Because beyond routine industrial hazards and safety considerations, LNG presents specific safety considerations. To consider potential LNG hazards, we must first understand the properties of LNG and the conditions required in order for specific potential hazards to occur. So, with regard to the LNG properties, LNG is an extremely cold, non-toxic, non-corrosive substance that is transferred and stored at atmospheric pressure. It is refrigerated rather than pressurized, which enables LNG to be an effective, economical method of transporting large volumes of natural gas over long distances. LNG itself poses little danger as long as it is contained within storage tanks, piping, and equipment designed for use at LNG cryogenic conditions. However, vapors resulting from LNG as a result of an uncontrolled release can be hazardous within the constraints of the key properties of LNG and LNG vapors: flammability range and in contact with the source of ignition. Moving to the potential hazards of the LNG. The potential to operators of LNG facilities and surrounding communities from the basic properties of natural gas power. First of all, case of an explosion. Could you close your microphone, please? Όχι, από εδώ το κάνουμε μόνο συνήθως. Resuming back on the potential hazards. The first potential hazard is an explosion. An explosion happens when a substance rapidly changes its chemical state, in other words, is ignited or is uncontrollably released from a pressurized state. For an uncontrolled release to happen, there must be a structural failure, meaning that something must puncture the container or the container must break from the inside. LNG tanks store the liquid at an extremely low temperature, about minus 256 Fahrenheit or minus 160 degrees Celsius, so no pressure is required to maintain its liquid state. Sophisticated containment systems prevent ignition sources from coming in contact with the liquid. Since LNG is stored at atmospheric pressure, in other words, it's not pressurized, a crack or puncture of the container will not create an immediate explosion. Moving on to the vapor clouds hazards. As LNG leaves a temperature-controlled container, it begins to warm up, returning the liquid to a gas. Initially, the gas is colder and heavier than the surrounding air. It creates a fog, a vapor cloud, as might be said, above the released liquid. As the gas warms up, it mixes with the surrounding air and begins to disperse. The vapor cloud will only ignite if it encounters an ignition source while concentrated within its flammability range. Safety devices and operational procedures are intended to minimize the probability of a release and subsequent vapor cloud having an effect outside the facility boundary. Freezing liquid hazards. If LNG is released, direct human contact with a cryogenic liquid will freeze the point of contact. Containment systems surrounding an LNG storage tank, thus, are designed to contain up to 110% of the tank's contents. Containment systems are also separate the tank from other equipment. Moreover, all facility personnel must wear gloves, face masks and other protective clothing as a protection from the freezing liquid when entering potentially hazardous areas. This potential hazard is restricted within the facility boundaries and does not affect neighboring communities. Fourth potential hazard is the rollover. When LNG supplies of multiple densities are loaded into a tank one at a time, they do not mix at first. Instead, they layer themselves in an unstable strata within the tank. After a period of time, this strata may spontaneously roll over to stabilize the liquid in the tank. As the lower LNG layer is heated by a normal heat leak, it changes density until it finally becomes lighter than the upper layer. At that point, a liquid rollover would occur with a sudden evaporation of LNG that may be LNG safety and security. Too large to be released through the normal tank pressure release valves. At the same point, the excess pressure can result in cracks or other structural failures in the tank. To prevent stratification, operators unloading an LNG ship measure the density of the cargo and, if necessary, adjust their unloading procedures accordingly. LNG tanks have rollover protection systems which include distributed temperature sensors and pump-around mixing systems. Moving forward to the rapid phase transition potential hazards, where when released on water, LNG floats, being less dense than water and vaporizes. If large volumes of LNG are released on water, it may vaporize too quickly, causing a rapid phase transition. Water temperature and the presence of substances other than methane also affect the likelihood of an RPT. The rapid phase transition can only occur if there is a mixing between the LNG and water. Rapid phase transition ranges from small pops to blasts large enough to potentially damage lightweight structures. Other liquids with widely differing temperatures and boiling points can create similar incidents when they come in contact with each other. Moving to the sloshing potential hazards, where the advent of LNG offshore terminals implies certain risks associated with tanks only partially filled with LNG. Carrying LNG, in particular in partially filled tanks, could lead to sloshing, a violent motion of the fluid. Sloshing could lead to an increased high pressure of LNG on the tank walls, especially in an abnormally harsh wave environment. Possible sloshing effect might require additional modifications to LNG cargo systems, especially taking into account increasing size of LNG carriers. Several engineering organizations, including Det Norsk Veritas (DNV) and Norwegian Maritime Technology Research Institute, have projects underway researching this important safety issue. While finally, with regard to potential hazards, we have earthquakes and terrorism, where they include the unexpected risk of earthquakes and terrorism. Now, we're going to discuss some elements of safety in the LNG. Beyond the routine industrial hazards and safety concerns, LNG presents specific safety considerations. Safety in the LNG industry is ensured by 4 elements that provide multiple layers of protection both for the safety of LNG industry workers and the safety of the communities that surround LNG facilities. Additionally, these critical safety conditions are all integrated with a combination of industry standards and regulatory compliance. As we can see in the picture below, we see the 4 layers with the 4 safety layers in the LNG industry, which are complemented by industry standards and regulatory compliance, which we'll discuss in the next slides. Moving to the layers more specifically, we have primary containment is the first and most important requirement for containing the LNG product. The first layer of protection involves the use of appropriate materials for LNG facilities, as well as proper engineering design of storage tanks onshore and on LNG ships and elsewhere. Secondary containment ensures that if leaks or spills occur at an onshore LNG facility, the LNG can be fully contained and isolated from the public. We must note here that the term containment is used to mean safe storage and isolation of LNG. Moving to the third layer and the safeguard systems. In the third layer of protection, the goal is to minimize the release of LNG and mitigate the effects of release. For this level of safety protection, LNG operations use systems such as gas, liquid and fire detection to rapidly identify any breach in containment and remote and automatic shut-off systems to minimize leaks and spills in the case of failures. Operational systems with procedures, training and emergency response also help prevent or mitigate hazards. Regular maintenance of these systems is vital to ensure their reliability. LNG operations use technologies such as high-level alarms and multiple backup safety systems, which include emergency shutdown systems. With regard to the latter, ESD systems can identify problems and shut off operations in the event certain specified fault conditions or equipment failures occur, and which are designed to prevent or limit significantly the amount of LNG and LNG vapor that could be released. Fire and gas detection and firefighting systems all combine to limit effects if there is a release. The LNG facility or ship operator then takes action by establishing necessary operating procedures, training, emergency response systems, and regular maintenance to protect people, property, and the environment from any release. While the fourth layer of safety includes the separation distance, where LNG facility designs are required by regulation to maintain separation distances to separate land-based facilities from communities and other public areas. Safety zones are also required around LNG ships. Finally, all these layers, as we said earlier, are complemented and integrated with industry standards and regulatory compliance. Actually, no systems are complete without appropriate operating and maintenance procedures being in place and with assurance that these are adhered to and that the relevant personnel are appropriately trained. Organizations such as the Society of International Gas Tanker and Terminal Operators, Gas Processors Association, and the National Fire Protection Association produce guidance which results from industry best practices. Industry standards are written to guide industry and also to enable public officials to more efficiently evaluate safety, security, and environmental impacts of LNG facilities and industry activity. Regulatory compliance should ensure transparency and accountability in the public domain. Now, moving forward to the LNG value chain and the LNG facilities, we can see in this picture the LNG value chain, of which the major components include the following stages. The natural gas production, which is the process of finding and producing natural gas for delivery to a processing facility. Then we move to the liquefaction, where the conversion of natural gas into a liquid state so that it can be transported in ships. And we have the transportation leg, where the shipment of LNG in special purpose ships for delivery to markets. The process of regasification, where conversion of the LNG back to the gaseous phase by passing the cryogenic liquid through vaporizers. The distribution and delivery phase of natural gas through the national natural gas pipeline system and distribution to end users, while a major component of LNG value chain, which consists of the storage facilities, where it is a major focus for safety and security. Once natural gas is liquefied, it is stored before shipment or loaded directly into the ship. LNG ships are required to have double hulls by regulation of the International Maritime Organization to facilitate safe transportation by sea. LNG receiving terminals and regasification facilities store LNG before it is regasified for pipeline transportation. With regard to the LNG facilities, information on the critical features of major LNG facilities as they relate to safety and security should be provided. A typical onshore LNG facility, a typical onshore LNG receiving terminal and regasification facility like those that currently exist and the ones that are planned or proposed consists of marine facilities, LNG receiving and storage facilities, and evaporation facilities. As we see in the picture below, The flow of the LNG gas passes from several stages in order to end in the gas depot. From the marine facilities, it should be passed through a jetty or through a pipeline to the LNG receiving and storage facilities, and then on to pass from the evaporation facilities to be finally stored to the gas depots. More particularly, with regard to the marine facility, the LNG dock facilities are designed or must be designed to berth and unload LNG from ships. Tugboats provide assistance when berthing, while the dock should be designed to accept a specified size range of LNG ships. Then we have the LNG receiving and storage facilities, where once the LNG ship is moved and the unloading arms on the dock have been connected, the ship's pumps will transfer LNG into the onshore LNG storage tanks. Offloading generally takes about 12 hours depending on the cargo size. Double-walled tanks store LNG at atmospheric pressure. LNG, as we said earlier, is a cryogenic fluid and it is not stored at high pressures, so an explosion of LNG from overpressure is not a potential hazard. The issues regarding LNG storage tanks apply both to the liquefaction and regasification facilities because the storage tanks are of the same design. New technologies enable offshore LNG storage and regasification. While finally, we have the LNG evaporation facilities. Each LNG storage tank has sent out pumps that will transfer the LNG to the vaporizer. Ambient air, seawater at roughly 59 Fahrenheit degrees or 15 Celsius degrees, or other media such as heated water can be used to pass across the cold LNG through heat exchangers and vaporize it to a gas. Typical types of vaporizers that have been used worldwide for LNG regasification are open rack vaporizers, submerged combustion vaporizers, ambient air vaporizers, and finally intermediate fluid vaporizers. Now, with regard to the types of vaporizers used in the LNG facilities, open rack vaporizers and submerged combustion vaporizers are the most common vaporization methods in existing regasification terminals, which have generally been located in sub-equatorial regions. Recent LNG receiving terminal activities have been shifting to the equatorial region where the weather is warmer, and the use of intermediate fluid vaporizers is found to be attractive. Important factors that should be considered in the LNG vaporizer selection are the site conditions and the plant location, the availability and reliability of the heat source, customer demand fluctuation, emission permit limits, regulatory restrictions with respect to the use of seawater, vaporizer capacity and operating parameters, safety in design, operating flexibility and reliability, while finally capital and the operating costs. Now moving to the LNG operations procedures. First of all, we discuss the transfer procedure. So, the bunkering procedures should aim at establishing a safe and time-efficient track-to-ship bunkering procedures for LNG, encompassing the entire bunkering operation, both the operational bunkering process and the technical solutions needed. Therefore, certain conditions and requirements are needed. First of all, the approval. Before commencing any bunker operations, it is necessary to have the Coast Guard's approval for LNG bunkering, while secondly, there should be a ship and supplier compatibility. In other words, it must be clarified that mooring and bunker equipment are compatible in design so that the bunker operation could be conducted in a safe way before commencing any operation. The following points are to be confirmed by communication. Possibility for safe and effective mooring immobilizing of the tracks. The relative freeboard difference. The type and size of hose connections and manifold flanges. Connection order of the manifolds. Compatibility of ESDN communication systems. Operational envelope, which includes motions, weather, and visibility. X zones, hazardous zoning and ventilation. Field protection systems, where trip tray arrangements and water sprays for ships with different draft, while finally, compatibility of safety management systems. The transfer area. Thirdly, we have the transfer area. The transfer area is determined and approved by the Coast Guard. Points to be considered include the safety zone, the waves, the current swell and weather conditions, the tidal conditions, the maneuvering space or turnaround space, simultaneous operation during LNG bunkering. Fourth, we have weather conditions, as weather and current forecast for the area are to be studied before commencing a bunkering operation. Fifth element, which has to be considered before commencing bunkering operation, are the light conditions. The bunkering operation will be accomplished during the shutdown period overnight without passengers or vehicles on board the vessel. The shutdown occurs after dark. Intrinsically, safe light is provided at each terminal where bunkering will occur. Sufficient light is required in all hazardous and safety zones on board and on shore, as well as for all the open-air transfer lines, which requires monitoring during the filling operations. Finally, further on, we have the warning signs, where there shall be warning and instruction signs posted around hazardous areas of the vessel. The signs are to be placed clearly visible and according to an accepted guideline for placement of warning signs. The warning signs are to cover the risk of handling cryogenic liquid, fire, and safety issues, and show restricted areas. Now, with regard to some safety issues concerning the operational transfer procedures of LNG, we should know that the chief engineer is at all times responsible for the bunkering operation and should not allow safety issues to be influenced by the actions of others. They are to ensure that the correct procedures and checklists are followed and that safety standards are maintained and that the ship system and procedures are according to approved rules and regulations. X zone and hazardous zone. The bunkering area is to be an X-classified and restricted area during bunkering. Only authorized personnel are allowed in these areas during bunkering, as the terminal must establish a prohibited zone with warning signs to secure the bunker operation area. The size of the X zone shall be according to the IGF code for Zone 1. Special attention must be given to existing equipment such as the high voltage cables and their insulation and protection. The Zone 1 is within 3 meters or 99.8 foot of any bunker manifold valve, flange or gas tank outlet. Use of X-proof tools is decreed while in the X zone. It should be very clearly communicated that storage of combustible waste within the X zone and hazardous zone is prohibited. There should be adequate means, marking of equipment, fences, and X signs, such that safety of the operation cannot be affected by unauthorized personnel. Inside these zones, all electrical equipment is required to be strictly safe. Vessel and terminal staff should not carry any lighters, cell phones, or other portable electronic devices. Recommended protective equipment generally concerns face shield, hearing equipment, gloves, protective overall, protective footwear, and other equipment, which are strictly safe. ESD system. In the case that a hazardous situation, operational malfunction or security violations occurs, appropriate safeguards shall be implemented in order to detect that a release has occurred, reduce immediate consequences, and prevent escalation. Each track and ferry shall have an independent emergency shutdown system for a quick and safe shutdown of the transfer pump and all bunkering system valves in the case of emergency. The ESD system shall be appropriate for the size and type of the facility and shall be activated by some or all of the following situations: when gas is detected or fire is detected, when manual activation from ship and facility, ship drift movement of supply vehicle, when we have a power failure or a high level in the receiving tank, or any other abnormal pressure in the transfer system. Then we move forward to the checklist. Each ship is to have internal individual checklists for before, during, and after bunkering. For the bunkering operation, there shall be a common checklist which is to be filled out and signed by responsible operators on the track and ferry before operation is commenced. Then we have the instructions or the routines, where there shall be written detailed instructions for the bunkering process with regards to the responsibility and actions to be made in case of a malfunction or emergency. These instructions are to be quickly available at all times, and all personnel involved in bunkering operations are to be familiar with the content and location of the instructions. The instructions should cover the following areas: loss of communication or control system, loss of power, handling of cryogenic products, including the use of personal protection equipment and X-proof tools, ice formation and awareness of sharp edges, waves and weather conditions, while also collision and impacts from ships or trucks. Now we're going to make a 15 minutes break and we'll continue with the rest of the presentation. Thank you very much.